It's time for Maths with Mr. Thomas.
Here we go! Chapter 13, lesson number 7, the scalar product. Now what we've done in the past is we have multiplied vectors, but we have only multiplied them by a scalar. What we're going to do now is we're going to multiply two vectors together, such as a and b, and if we do that, well, we will get either a scalar or a vector. Multiplying vectors a and b together to result in a scalar, the way you write that is you would have vector a dot vector b. Note the dot. It is very important. So you're multiplying vectors a and b together. If you have the dot, you will end up with a scalar, and the result is known as the scalar product, or sometimes the dot product because of this dot. What you can also do is you can multiply two vectors together. So if you multiply a and b, multiplying them together to result in a vector, well, the way you write that is you would write down a, and then you would have your time sign, and then vector b. If you have the time sign and you're multiplying them together, then the result will be known as the vector product. However, the vector product is going to be introduced in advanced higher maths, so this is something that you do not have to worry about just yet. The only part that comes into higher maths is the scalar product, so you're going to have a dot b, and that is what we're going to look at just now. So, the scalar product then. Scalar product, the way you write it is a dot b, as we just showed on the last page, and it is worked out using a formula. The formula for the scalar product is a dot b equals, and it's going to be the magnitude of a times the magnitude of b times cos theta. What is theta, I hear you ask? What's theta? Well, theta is the angle between the two vectors a and b. For example, you have a vector a, you've got vector b, and theta is the angle between them. Theta will be between 0 and 180 degrees. Few notes here. First note is that the vectors must always be tail to tail. So you can see here they're pointing away from the vertex, and they must always be like that before you work out a dot b. Also, when you multiply them together, it's very important that the result is going to be a scalar. It is not a vector. That is something we will look at in advanced higher maths. Just now, we're multiplying them, and we will end up with a scalar. Also, note number 3, if a and b are perpendicular, then if you work out the scalar product, you will end up with 0. Because perpendicular means they're going to be at 90 degrees, and in the formula you would have the magnitude of a times the magnitude of b times cos 90. And cos 90, as I'm sure you're all aware, is 0. So really, you're going to have something times 0, and you just end up with 0. So if the vectors are perpendicular, then a dot b will equal 0. Sometimes though, this is the formula you would use, but a lot of the time you may not have the angle. So you may have your two vectors but not know the angle between them. And in that case, we're going to have to do something else. So that is the formula that we just had. As I said, sometimes you do not know the angle, so what we're going to have to do is use a different formula. Imagine if you had two vectors, say they were in component form. So we had vector a, which is going to have the components, just a1, a2, a3, and vector b with the components b1, b2, b3. You can also work out the scalar product using this formula. So a dot b equals, and you're going to take the first components and multiply them together, take the second components, multiply them together, and then take the third components, multiply them together, and then you're going to add the result of them all. So there are two formulas for the scalar product. You have the first one up here and the second one down here. Let's try some examples then. So example 1, using these formulas, or one of them, whichever one we would use, calculate a dot b for each of the following. So we have a, b, c, and d. We've got a couple of vectors. We've got the angle between them. We're wanting to multiply the two vectors and end up with a scalar product. Let's do them one at a time. So example 1a. We've got vector a, we've got vector b, there's 60 degrees between them. We know the length of a is 4 units, the length of b is 3 units. So to work out a dot b, the scalar product, you're going to have a dot b equals the magnitude of a times the magnitude of b times cos theta. In this case then, we are going to have The magnitude of A is just 4, that's 4 units. We're multiplying that by the length of B, which we can see is 3 units, and we're going to multiply that by cos of theta, and theta is going to be 60! Brilliant! So you've got your 60 degrees. From there then, well, 4 times 3 works out as 12, and cos of 60 for this, if it was a calculator paper, you could just stick it into your calculator, but you should be able to work this out with exact values. Think about your exact value triangles, and the cos of 60 is 1/2. From there, a half times 12, or a half of 12, is just going to be 6. The result, remember, is a scalar, not a vector. So that is your scalar product. Example B, we've got A and we've got B. We're wanting to work out A dot B. So once again, we are thinking A dot B equals the magnitude of A times the magnitude of B times cos theta. Working this out, well, we would take whatever the length of A was, take whatever the length of B is, and multiply that by cos theta. What is theta this time? Brilliant, it's going to be 90 degrees. So you've got cos 90. And cos 90 works out to be 0, good. So you've got the magnitude of A times the magnitude of B times 0. And whenever you multiply anything by 0, you just end up with 0. So that is going to be your answer. Remember the second note that I introduced a minute or two ago. If A and B are perpendicular, which you can see here, they are at right angles, then A dot B is going to be 0, since cos 90 works out to be 0. Let's try another one. Example 1, part C. So once again, we have two vectors. We've got A, we've got B, we've got 120 degrees between them, and we know the length of both A and B. To work out A dot B, we've got the formula. A dot B equals the magnitude of A times the magnitude of B times cos theta. So the magnitude of A is going to be 2. The magnitude of B, just the length of B, is going to be 1. And we're multiplying that by cos 120 degrees. From there, again, if it was a calculator paper, you could just type that in, or you could start working it out using exact values. If you're unsure about your exact values, about why cos 120 is the same as negative cos 60, look back to the lesson on exact values. But really, you're thinking 120 degrees would lie in the second quadrant. In the second quadrant, cos is a negative, so you get negative cos, and the distance from 180 degrees, the size of the acute angle is 60, so it becomes negative cos 60. From there, the 2 times 1 was just 2. Multiply that, and that will give you 2 times, and negative cos 60. Cos 60 is a half, so we'd have negative a half. So it's negative a half times 2, which is negative 1. And that will be your answer. Let's try another one. So example 1, part D. What do you notice about this one? What is different? Help us out, Chelsea. Yeah, the vectors are not tail to tail. Look at this one. So one arrow is pointing towards the vertex and the other is pointing away. Dun, dun, dun. So what do you have to do in this case? Well, the vectors must always be tail to tail. Remember though, vectors are equal if they have the same length and the same direction. So let's say we took this vector B and we're sliding it down here. So it's still got the same length, it's still got the same direction. And if we do that, then we will end up with something that looks a bit like this. The length of A, we are not changing. The length of B, again, we are not changing. We're just sliding that vector down, so they are now tail to tail. The angle, though, it was 45 degrees when B was up here. But now if you slide it down, well, really it's that straight line there. So 180 take away the 45 degrees gives you 135. So now we have two vectors. They are tail to tail. There's 135 degrees between them. And we know the length of each. So we can think A dot B equals magnitude of A times the magnitude of B times cos theta. Working that out then, the length of A is 2 root 2, the length of B is 3, and we're multiplying that by cos. Which angle do we use? Good, 135 degrees. From there, you can think, right, well, 2 root 2 and 3 would really stay as they are, but the cos of 135 degrees. That would lie in the second quadrant where cos is a negative, and the distance away from 180 degrees is 45 degrees. That would be your angle. From there then, use your exact value triangles for cos of 45 degrees. That would give you 1 over root 2. So really you would have 2 times 3 is 6, and you've got the root 2. And remember the negative, you would have negative 1 over root 2. Multiply them together, well really the root 2 and divide by root 2 would cancel out, leaving you with negative 6. And that would be your answer. Woo! Let's try another one. Example 2. Calculate the exact value for a dot b for this diagram. So again, you have two vectors. We have a and we have b. They are tail to tail, just like that. And you know the length of a is 4 and the length of b is 5. The angle between them is 5 pi over 6. So going straight into this then, working out a dot b, well, we know the size of the angle, so we can use the magnitude of a times the magnitude of b times cos theta. Working that out then, the length of a is 4, the length of b is 5, and we multiply that by cos. What would the angle be here? Good, 5 pi over 6. Excellent. So working this out, what may make it easier for you is rather than working out cos of 5 pi over 6, think about what that would be in terms of degrees. Remember, pi is the same as 180 degrees. So I would do 180 divided by 6, and then times that by 5. Or you could do 180 times 5 and divide it by 6. Either way, that's the same as cos of 150 degrees. From here, 150 degrees is in the second quadrant, where cos is a negative, so that will be the same as negative cos, and the distance from 180 is 30 degrees. 4 times 5 gives you 20, so it's 20 times negative cos 30. Use your exact value triangles, and the cos of 30 is... brilliant. It becomes negative root 3 over 2. From there then, you would end up with negative 10 root 3. And that would be your answer. That is your scalar product. Let's try another one. Example 3. If A has the components 1, 2, 5, and B has the components negative 1, 1, negative 2, find A dot B. What do you notice about this one? What is different about it, Sohana? Yeah, we are not given the angle. We're not told the angle, so we cannot use this formula here. We cannot use a dot b equals magnitude of a, magnitude of b cos theta, because we don't know what theta is. So we have to use this formula. And this is really the one you would use if your vectors were written in component form, because you're just multiplying the first two components, multiplying the second components, multiplying the third, and then adding them all together. So in this one here, as it says, no angle is given, so we have to use the second formula. From that then, you would have a dot b equals a1 b1 plus a2 b2 plus a3 b3. From there, you would do 1 times negative 1. You're adding on 2 times 1, and then again add on 5 times negative 2. Simplifying that, you get negative 1 add 2, take away 10, and that becomes negative 9. So that will be your answer. Woohoo! Let's try another one. Example 4, if A equals 3i minus 2j plus k, and B equals 2i minus k, find the scalar product, A dot B. So for this one, what would you do first of all? Help us out, Sufyan. Sufyan, you are the man. Well done. Think about these in component form. So for this, A has the components 3, negative 2, and 1 is really the coefficients of I, j, and k. B, you would have the coefficients again of I, j, and k. So the coefficient of I is 2. J, well, there is no j. And you would have negative k, so it would be negative 1. So we are thinking about them in component form first of all. After that, which formula would you be using? Brilliant. You would have to use the second one up there because no angle is given. So from this, you can have a dot b equals a1 b1 add a2 b2 add a3 b3. From there, multiply the first two components, so 3 times 2. Add on negative 2 times 0. Add on 1 times negative 1. Simplifying that, you get 6 add 0. Take away 1, which is going to give you 5. So that will be your scalar product. Let's try another one. Example 5, given P, which is 158, Q, which is negative 2, 1, 3, and R, which is 1, negative 6, is 0. If PQ represents U and QR represents V, then calculate U dot V. So again, we're wanting the scalar product. So we want to work out U dot V. What you should realize, first of all, is that you're needing to have two vectors really in component form. We don't know the angle here, so we're going to have to think about the components. To get the components of U, how would you do that? Good, it's telling you U is going to be PQ, and to work out PQ, well, that is going to be Q minus P. So in other words, we're going to have negative 2, 1, 3, take away 1, 5, 8, meaning the component form for u will be negative 3, negative 4, negative 5. Do the same thing for v. What is v? Well, that is QR. And to work out QR max, what would you do? R minus Q. Good, well done. And if you put in the vectors, you will end up with 1, negative 6, 0, take away negative 2, 1, 3, giving you 3, negative 7, negative 3. From there, what would you do? Aaron, help us out. Excellent, well done. So no vector is given, so you're going to have to use v dot u equals v1, u1 plus u2, v2 plus u3, v3. From there then, really multiply the x values together, multiply the y values together, multiply the z values together, and then add the results together. So from that, you would have negative 3 times 3, add on negative 4 times negative 7, add on negative 5 times negative 3. Working that out, you get negative 9 plus 28 plus 15, which equals 34! Woo! And that is your answer. Example 6. S is 1, 2, and negative 3, and t is 11, and negative 3, 7. U divides st in the ratio 3 to 2. Find first of all the coordinates of u, and secondly the value of su dot ut. So first thing we have to do is find the coordinates of u. It's saying u divides st into that ratio. If you think back a couple of lessons, well, we were dividing a line into a given ratio using the section formula. So for that, I just start off writing down what I know. So you're going to have a line, you're going to have s and t at one end, and u is going to be somewhere in between. So you know from s to u, and then from u to t, that would be the ratio 3 to 2. We also know the coordinates of s, and we know the coordinates of t, so I'm thinking about everything I know. From there, if a point does divide a line into a given ratio, you're thinking about the section formula. That is the formula for the section formula, which is not given in the exam, so I prefer thinking about this wee diagram. You're going to have the points a and b, you're going to have the ratio m to n, and point p will lie somewhere in between them. In this case though, we don't have a and b, we've got s and t, and we have the ratio 3 to 2. And the point between them is called u. So we've got u. If you work that out then, well, u, the vector u, the components to work that out, you're going to be doing 2 times s. So it's going to be 2 times vector s, which is 1, 2, and negative 3. You're going to be adding on 3 times the components of t, so 3 times 11 and negative 3, 7, and you're going to be dividing that by m plus n, so 3 plus 2. Working that out then, you're going to have 2 times this vector, 3 times this vector, which will give you these vectors here, and we're going to be dividing that by 5. Work that out then, if you add these 2 vectors at the top, add the x's, the y's and the z's, you will end up with 35, negative 5, and then 15, and we're dividing that by 5. Really what you're doing is you're multiplying this vector then by a fifth, so you're just taking a fifth of 35, you're taking a fifth of negative 5, and a fifth of 15. That then will be the vector u, and to work it out, just as coordinates then, you will have 7, negative 1, 3. Woo! Let's try part B. So for part B, we want to work out the value of su dot ut. So to work that out, well, we already know the coordinates of u. We just worked that out in part A. We've got 7 and negative 1, 3. So before we can multiply the 2 vectors together, we need to get the components for su. So su is going to be u minus s. So you've got 7, negative 1, 3, take away 1, 2, negative 3. Working that out, you get 6, negative 3, 6. Do the same thing for ut. So ut is going to be t minus u. Giving you then 11, negative 3, 7, take away 7, negative 1, 3. Meaning you will have the vector 4, negative 2, 4. Just like that. After that, where would you go from there? What would you do, Grace? Yeah, you want to use the formula. The formula we'd use this time to get the vector scalar product. You would use a dot b equals a1b1 plus a2b2 plus a3b3. Really, you're multiplying the components together. So for this then, to work out su dot ut, you will have 6 times 4 plus negative 3 times negative 2 plus 6 times 4. Simplify that and it gives you 24. Add 6, add 24, which, Grace, will give you 54. Brilliant. And that will be your answer. Let's try one more. Example 7. Find the value of I.j plus k.k. That is all we are told. Who thinks they can help us out here? Sandy. Thank you. What would you do, Sandy? Yeah, brilliant. These are your unit vectors. I, j, and k are your unit vectors. Remember when we introduced them just at the start of this chapter, we had vector I, which was 1, 0, 0. And really, it's going to be the point 1, 0, 0 there. It's a vector with 1 unit of length. And it's going in the x direction. Vector j has again 1 unit of length, and it is just going to be going in the y direction. And this vector here, k, is going in the z direction, and again it's 1 unit long. So to work this out then, if you think about this, you want I.j plus k.k. Well, really what you're wanting to do here is you're wanting the magnitude of I times the magnitude of j times cos of the angle between them. And the angle between I and j, one is really your x-axis, one is your y-axis. The angle between them is 90 degrees. So you'd have cos 90. Do the same thing with k.k. Well, really, that's just going to become the magnitude of k times the magnitude of k times cos. If you think about this, if you've got two vectors, the same length and the same direction, well, really, the angle between them is just going to be 0. Really, the vectors will just be on top of one another. Working that out then, the length of I, well, it's your unit vector, so it's just got a length of 1. J also has a length of 1, and the cos of 90 is 0. Good. And do the same thing with this part here. So you'd have k dot k, the magnitude of k times magnitude of k, giving you 1 again. It's got a unit vector. It's got a length of 1. Again, it's a length of 1. And the cos of 0 is 1. Brilliant. Well done. From there then, 1 times 1 times 0 is 0. And you're wanting to add on 1 times 1 times 1, which is just 1. And 0 add 1. I'm sure everybody can do that. You just get 1. So that will be the value of I.j plus k.k. That is it. 7 examples. That is your scalar product. You're multiplying two vectors together and you're ending up with the result, which is a scalar. Try some of these questions in the Maths in Action book. It's page 209, exercise 8. Check your answers as you go. Any problems, let me know. Have fun with them. Woo!